Hello, my name is Mohan Kalkunte. I am the VP of Architecture and Technology in the switching group at Broadcom. Today I want to explain to you about NPL, a new data plane language. NPL stands for Network Programming Language. I want to explain why we embarked on this journey. But first, let's look at the switch stack and how that has progressed in the last few years. So if you look at the switch stack, a traditional switch stack, you have an ASIC, you have a driver, you have an OS, and applications. What has happened over the course of years is this has gotten disaggregated. So you have an ASIC, like a merchant ASIC, like Broadcom. The driver that ASIC provider provides, which is also, in some instances, this is also open. You have many network operating systems like Sonic, FBOSS, etc. So these are open network operating systems. And of course the applications, the control applications. So what has happened is what was vertically integrated has gotten disaggregated, as well as the control plane is decoupled from the data plane. Now, with the control plane being decoupled from the data plane, that allows, for instance, an SDN controller to remotely come and configure the data plane. Now, OpenFlow was a protocol that was developed it was a wire protocol that was developed to enable to configure an ASIC. Now, OpenFlow was based on, it was a table-based semantic, and what was one of the problems with OpenFlow was it was very difficult to express complex functionality using OpenFlow. At Broadcom, we have embarked on programmable data planes for several years now. So starting in 2010, we had the DNX line of devices, which it was called Petra and Arad. So these devices back then had programmable stages. So we could do in-field upgrade like VXLAN, for instance. Then in 2015, 2017, we introduced Jericho, which is another DNX line of product. We also introduced Trident 3. And in 2018, 2019, we introduced the follow-on to these products, which we call it as Jericho 2 and Trident 4. So the DNX line of products, Petra, Arad, Jericho, and Jericho 2, have continuously evolved in their programming capability. So there were few stages that were programmable here, more stages in Jericho, and some more stages. So in Jericho 2, all the stages, the pipeline stages, are fully programmable. In Trident 3, back in 2017, we introduced a semi-programmable blocks. Some stages were programmable, followed by Trident 4, where we made it fully programmable. So again here, there were several features like VXLAN over IPv6, PPP over E, um, in-band telemetry. So all these features were introduced after these devices were in production. Both Jericho 2 and Trident 4, these are fully compiler-driven architecture. When we embarked on defining the Trident 4 architecture, we had primarily two goals in mind. One is, how can you define an architecture that is very efficient in terms of scale, performance, features, as well as, you got to make sure it is economically, a better product. And the second one was, how can we define a data plane language that expresses the capability of such an efficient pipeline? So those were the two primary goals that we had when we were thinking about NPL. Now, we looked at P4 at that time. P4 was an evolving language, and it did not have all the constructs and features and capabilities that we needed so that it satisfies our metrics. Thus, NPL was born. At a high level, NPL provides the following capabilities. We have a basic set of constructs. I'll call this basic. So you have the basic capabilities like parse, rewrite, per table actions, etc. Now, in addition to this, NPL provides several additional advanced constructs. First one, what I call it as multi-lookup logical tables. So what does this mean? So let's say, for instance, let me give an example. Let's say, for instance, I have a table and I want to, let's say this is a layer 3 table. It's a hardware table. And I want to look up based on source IP address, and I want to look up based on destination IP address. So essentially, I'm doing two logical tables in a single hardware physical table. This is what we call as multi-lookup logical tables. This is something that we have an explicit construct in NPL to allow this. The second one, advanced parallelism. Any efficient architecture, you need to have certain amount of parallelism built into the pipeline to reduce latency. So as an example here, let's say you want to do bridging and routing. So you can do it in a serial fashion. So you can do a bridge lookup, and then determine whether it needs to be bridged or routed, and then do a route lookup. Or you could do something like bridge lookup, and you can do a route lookup in parallel, and then later on decide whether you want to route or bridge. Now this concept can be extended to many other applications, but this is the concept wherein you can do parallel lookups, but then determine what the course of action is later on in the pipeline. Another one is table independent actions. So basically what this means is when you look up a table, you get an action. That does not mean you have to carry the action right away. And you carry that action much later in the pipeline. And this is part of the action processing, which I'll talk about a little bit later. fourth one, what we call as strength-based resolution. Now in the strength-based resolution, you can assign certain strength to each of these tables. So let's say you're doing several lookups in the pipeline, and for each of those table lookups, let's say we provide some strength. And then later on in the pipeline, you can resolve based on the strength or the relative strength between those lookups as to which course of action you need to take. So that's the concept of strength-based resolution. Another construct that we support programmable microengines. So sometimes in the pipeline, we want to have some efficient microengines. So these are hardware engines. So for example, hashing as an example, which is used in ECMP, lag resolution, and so on. We want to have these efficient hardware implementation. The inputs to that such an engine is programmable. The output of that is also can be flexibly interpreted, and all of these can be defined in the NPL by the user. The next one is function primitives. So when you do things like multi-lookup logical tables, you do advanced parallel lookups, or you do strength-based resolutions, or you do ACL lookups, or you get outputs from your programmable microengines, all of these things needs to be resolved, and those are resolved by what we call as functions. So we can write complex if-then-else statements to resolve what exactly needs to be done in the packet depending on all the lookups that has happened, and all of these are specified by the NPL user. The next one is advanced instrumentation. So instrumentation is very key to the device, and we have added constructs in the NPL to support things like packet trace, packet drop, so that you get more visibility into the device. And again, this is specified by the NPL user or the NPL developer. And last but not least is runtime programmability. So this is very key. So let's say, for instance, while the device is up and running in the field, and you want to attach some objects of interest. So let's say there is a congestion, and you want to attach some counters to those objects of interest. You don't have to recompile the data plane in that case. Or let's say you want to create a new dynamic table. Again, you don't want to recompile the profile again. So all of these capabilities are provided during runtime programmability, and we have several constructs here that allows you to do a lot of things while the device is running, and that does not require a new data plane profile. As you can see, NPL has quite a bit of capability packed into it to build a very efficient silicon architecture. NPL is supported both on Jericho 2 as well as on Trident 4. And in Trident 4, it has all the capabilities, takes advantages of the advanced constructs in the NPL so that you have a very efficient silicon architecture. NPL is an open language. More information on NPL can be found on nplang.org. The tools are available on GitHub. I invite you to try NPL.